November 10th, 1941. Las Vegas Army Airfield, Nevada. Inside a concrete hangar, young recruits studied an instructor's chalkboard, filled with vector diagrams, arrows crossing at impossible angles, numbers calculating what seemed wrong. Outside, mock turrets swiveled to track film-projected enemy fighters, and trainees missed nearly every shot. Army Air Forces commanders expected airborne gunnery to translate naturally from hunting and sport shooting: aim at the target, pull the trigger, hit what you see. Reality proved different. Early training reports showed hit rates below 10%. Men who could drop ducks from the sky could not touch fighters crossing at 300 miles per hour. The mathematics said something counterintuitive. To hit a moving target from a moving platform, gunners had to aim where the enemy was not. They had to aim behind the target. Within months, this counterintuitive lesson would double American kill rates and change defensive air warfare forever. Aircraft machine guns fired bullets that traveled roughly 2,850 feet per second from the muzzle of a Browning AN-M250 caliber machine gun. But those bullets inherited the velocity of the bomber carrying them. A B-17 Flying Fortress, cruising at 220 miles per hour, 323 feet per second, meant every round, leaving the gun already moved forward at that speed before adding its own muzzle velocity. The bullet's actual velocity through space combined these two vectors in ways that defied intuitive understanding. When an enemy Messerschmitt Bf 109 crossed perpendicular to the bomber's path at 400 miles per hour, simple physics created a geometric puzzle that confused even experienced marksmen. The fighter traveled 587 feet per second. At a range of 1,000 feet, the bullet required approximately 1/3 of a second to reach the target. During that third of a second, the enemy fighter moved nearly 200 feet, the length of 2 railroad cars. Aiming directly at the target meant hitting empty air 200 feet behind it. But the counterintuitive part confounded every recruit. From the turret gunner's perspective inside the moving bomber, compensating for that 200-foot deflection meant aiming at a point that appeared to be behind the target's current position. The bomber's forward motion carried the gunner and his weapon toward the interception point, so proper lead required aiming backward relative to the target's apparent motion across the sky. Human brains evolved to track prey animals running across open plains. Nothing in evolutionary history prepared men to calculate three-dimensional vector solutions while sitting in pressurized turrets at 25,000 feet. Training officers at Las Vegas Army Airfield faced a problem with profound implications for American air strategy. The Army Air Corps, soon to be redesignated as the Army Air Forces, planned to send hundreds of heavy bombers deep into German-controlled Europe without fighter escort. The B-17 Flying Fortress and B-24 Liberator would defend themselves through massed firepower. 10 50 caliber machine guns positioned in nose, dorsal, ventral, waist, and tail positions. Each bomber carried approximately 4,000 rounds of 50 caliber ammunition distributed among these positions. A typical bomb group of 36 aircraft put 360 machine guns in the air simultaneously, theoretically capable of creating impenetrable defensive fire. But theory required trained gunners who could actually hit attacking fighters. If defensive gunnery remained at 10% effectiveness, losses would become catastrophic. Luftwaffe fighter groups had demonstrated their capability against British bomber formations throughout 1940 and 1941. German pilots perfected attack techniques that minimized their exposure to defensive fire while maximizing damage to bombers. Me 109 seconds and 190 seconds attacked from 12 o'clock high, diving through formations at closing speeds exceeding 600 miles per hour, firing 20mm cannon and 13mm machine guns in concentrated bursts before breaking away. Without effective defensive fire, such attacks would shred American bomber formations. December 8, 1941. Pearl Harbor's smoking ruins intensified everything. Training Command received orders to accelerate gunnery programs while maintaining quality standards. The timeline compressed brutally, transformed civilians into combat-ready aerial gunners in 6 weeks. Scale the program to produce thousands monthly. Achieve measurable improvement in hit rates. Failure meant either unacceptable bomber losses or abandonment of daylight strategic bombing doctrine. American air power strategy rested on the assumption that heavily armed bombers could penetrate enemy airspace, strike industrial targets with precision, and return home despite enemy opposition. That assumption required gunners who could shoot. Las Vegas Army Airfield became the experimental center for solving the deflection problem. Lieutenant Colonel Harold R. Harris commanded the Flexible Gunnery School, overseeing development of training methods that would eventually spread to bases across America. Harris understood the challenge. He needed to teach physics to men who barely completed high school, override instincts developed over lifetimes, and produce consistent results under stress. His instructors included mathematicians, engineers, and experienced pilots who understood both the theory and practical application of deflection shooting. The curriculum began with fundamentals. Classroom sessions covered vector mathematics using simple diagrams that even poorly educated recruits could grasp. Instructors drew bomber velocity vectors on chalkboards, then added bullet velocity vectors, then overlaid enemy fighter velocity vectors. The intersection point where all three vectors met became the aim point to the empty space in the sky, where bullets and target would occupy the same position simultaneously. Recruits memorized standard deflection angles: 30 degrees for 12 o'clock high attacks, 50 degrees for 3 o'clock beam attacks, minimal deflection for 6 o'clock stern attacks from level flight. These memorized values gave gunners starting points for calculations they would refine through experience. Instructors emphasized the relationship between range, closing speed, and deflection angle. At 500 yards, a fighter crossing at 400 miles per hour required roughly 30 degrees of lead. At 1,000 yards, the same target needed nearly 50 degrees. Closing head-on attacks required maximum deflection because relative velocity reached 800 miles per hour or more, bomber speed plus fighter speed. Stern attacks from directly behind needed minimal deflection because both aircraft moved in the same direction, dramatically reducing relative velocity. Understanding these principles separated effective gunners from men who simply blazed away hoping for lucky hits. Ground training incorporated technology that barely existed before the war. The Waller Gunnery Trainer represented a marvel of analog computing, a device that projected moving aircraft images on a dome screen, while gunners sat in realistic turret mock-ups. As trainees tracked projected targets and squeezed their triggers, an electromechanical computer calculated whether each burst would have resulted in hits based on lead angle, range estimation, and tracking smoothness. Instructors could adjust attack speeds, ranges, and angles to create thousands of realistic scenarios without expending ammunition or risking aircraft. Each trainee fired approximately 5,000 simulated rounds during the ground training phase, more than many combat gunners fired during entire tours of duty. The Waller trainer provided immediate feedback through lights and scoring displays. Missed shots lit red indicators, while successful deflection produced green lights and recorded hit counts. Instructors observed from control stations, noting which recruits struggled with specific attack profiles and providing targeted remedial instruction. The system worked because it removed consequences while preserving geometry. Men could fail repeatedly without danger, learning from mistakes in ways impossible during actual aerial gunnery, where errors meant empty sky and wasted ammunition. Psychological research would later confirm what instructors discovered empirically. Humans learn complex motor skills faster through repetitive practice with immediate feedback than through dangerous trial and error in real conditions. Classroom sessions reinforced simulator training with detailed analysis, Instructors froze attack sequences at critical moments, asking recruits to estimate proper lead angles before revealing correct solutions. This constant drilling internalized the counterintuitive calculations required for deflection shooting. Men who initially insisted they couldn't aim behind targets gradually accepted the mathematics. Their brains began processing three-dimensional intercept geometry automatically, translating visual input into muscle commands without conscious calculation. The transformation occurred gradually, but measurably, through standardized testing protocols. Range work added realism and built confidence. Skeet shooting ranges became part of the standard curriculum because shotgun sports taught angular lead principles without the complication of platform motion. Instructors noted that recruits from rural hunting backgrounds often adapted faster than city boys with no shooting experience, but the advantage disappeared after a few weeks of training. Systematic instruction overcame natural aptitude, proving that deflection shooting could be taught rather than inherited. This discovery had profound implications. America could train vast numbers of competent gunners, regardless of their backgrounds or pre-military experience. March 5, 1942. Nevada desert ranges provided the final validation. A Douglas A-20 TOW aircraft unreeled a fabric sleeve target measuring 6 feet by 30 feet on a quarter-mile steel cable. The sleeve flew approximately 200 feet per hour slower than the tow plane, creating realistic target motion. B-17 seconds and B-24 seconds made practice passes with live .50 caliber ammunition, while range officers observed from protected positions. Each gunner fired rounds with colored tips, red for gunner 1, blue for gunner 2, green for gunner 3, and so on, allowing officials to score individual performance by examining the bullet holes in recovered sleeves. Results exceeded all expectations. Gunners who completed the full 6-week curriculum, 100 hours classroom, 80 hours simulation, 40 hours aerial practice, averaged hit rates near 50% against towed sleeves. This represented a 5-fold improvement over untrained recruits who rarely exceeded 10%. The improvement was not marginal but transformative, turning defensive gunnery from desperate hope into reliable capability. More significantly, trained gunners maintained consistent accuracy across multiple attack profiles. They hit crossing targets as reliably as stern approaches, demonstrating that they understood principles rather than memorizing specific sight pictures. Performance remained consistent regardless of weather conditions, time of day, or stress levels during testing. The training methodology worked because it addressed fundamental physics rather than teaching situation-specific techniques. Ammunition conservation emerged as an unexpected strategic benefit that logistics officers quickly recognized. Pre-war doctrine assumed aerial gunners would need to saturate engagement zones with bullets, creating barriers of lead through volume rather than precision, essentially spraying the sky with metal and hoping enemy aircraft flew into the pattern. Calculated deflection shooting reduced ammunition expenditure per kill by approximately 60% compared to untrained baseline performance. Instead of firing 2,000 rounds hoping for lucky intersections with enemy flight paths, trained gunners fired 800 rounds with predictable results. For bombers carrying limited ammunition loads, approximately 400 rounds per gun position, less than 10 seconds of continuous fire. This efficiency meant sustained defensive capability throughout missions, lasting 8 hours or more. The difference between exhausting ammunition after one engagement versus maintaining capability through multiple attacks could determine mission success or catastrophic loss. Logisticians quickly grasped the implications. A bomb group of 36 aircraft carried approximately 144,000 rounds of .50 caliber ammunition total. At pre-training effectiveness levels, that ammunition load might produce 8 to 12 enemy kills per mission while lasting perhaps 30 minutes of sustained defensive combat. With trained gunners, the same load produced 20 to 30 kills and lasted through multiple engagement periods. This efficiency multiplied combat power without adding weight or reducing bomb loads. Training produced tactical advantages that engineering could not duplicate. Statistical analysis throughout 1942 painted an increasingly clear picture. Bomber groups with fully trained gunners reported loss rates 30% lower than groups with abbreviated training or pre-war trained crews. Enemy fighters downed per mission increased from an average of 0.2 to 0.4, exactly double the effectiveness. Camera gun footage confirmed the mathematical models. Successful engagements showed tracer rounds converging ahead of enemy flight paths, fighters flying into established fields of fire, strikes occurring where ballistic calculations predicted they would occur. The physics worked precisely as mathematics insisted it must. German fighter pilots noticed the change before Luftwaffe intelligence understood its significance. Experienced pilots flying against American formations in late 1942 reported increasing difficulty pressing attacks. Where early missions against American bombers had seemed almost easy, the defensive fire scattered and ineffective. Later raids encountered coordinated fire that forced attackers to break off or risk certain destruction. German loss rates against American bomber formations climbed from 5% per raid to nearly 15% by year's end. Luftwaffe commanders attributed the change to improved American tactics and better equipment, never suspecting that systematic training had transformed defensive capability. August 20, 1942, Tyndall Field, Florida. Training Command opened dedicated flexible gunnery schools across the United States, each capable of graduating 500 gunners monthly. The standardized curriculum spread from Nevada to Florida, Arizona, Texas, and a dozen other locations. Every school followed identical schedules: 100 hours of classroom instruction covering physics, aircraft recognition, and weapons maintenance, 80 hours of ground simulation using Waller trainers and skeet ranges, 40 hours of aerial gunnery firing at towed sleeves from various aircraft types. Graduation required minimum proficiency scores on each module, 70% accuracy on simulation, 60% hits on aerial targets. Men who failed repeated modules until they passed or washed out entirely. Industrial support scaled to meet explosive demand. Arms manufacturers delivered Browning AN M2 machine guns by the thousands. Production reached 100,000 units before war's end. Lake City Army Ammunition Plant in Missouri produced 3 billion rounds of .50 caliber ammunition annually by 1943, enough to supply training bases, operational units, and maintain strategic reserves. Film studios created standardized attack profile footage for simulation devices. Transportation networks moved trainees between schools, ranges, and operational units with assembly line efficiency. By late 1942, the training pipeline produced more qualified aerial gunners monthly than Germany graduated fighter pilots. American industrial capacity transformed a tactical problem into systematic solution. Instructors came from operational bomber squadrons, rotating back after completing combat tours. These veterans brought first-hand knowledge of what worked under actual conditions. They described German fighter tactics and emphasized crew coordination. By mid-1943, instructor candidates attended separate teacher training courses. The best instructors combined combat experience with analytical thinking men who understood both the why and how of deflection shooting. Cultural resistance persisted among some trainees. Men raised on hunting traditions resented being told their natural abilities were inadequate. Some dismissed physics lessons as academic nonsense. Instructors handled skeptics through demonstration rather than argument. After watching trained gunners consistently hit targets by aiming at empty sky, doubters usually accepted the technique. Those who refused washed out. Deflection shooting required gunners to override powerful instincts developed over human evolutionary history. Training emphasized sustained repetition until correct techniques became reflexive. Advanced training included high-pressure scenarios with noise, time pressure, and simulated combat chaos. Men who remained calm under simulated stress usually maintained effectiveness in real combat. January 12, 1943, Eglin Field, Florida. Operation Pinball introduced revolutionary realism through modified Bell RP-63 King Cobra fighters with armor plating and photoelectric sensors. Gunners fired frangible rounds, bullets designed to shatter on impact, at real pilots flying attack profiles at combat speeds. Sensors registered hits with flashing lights. Despite tens of thousands of sorties, Operation Pinball recorded 0 fatalities. The system demonstrated American engineering's ability to balance realism with safety. Gunners averaged 45% hit rates against manned targets, virtually identical to towed sleeve performance. Statistical officers compared pinball results with European combat reports. The numbers matched within 5 percentage points. Deflection shooting worked in combat exactly as in training. Pinball exercises also revealed problems simulation couldn't expose. Some gunners froze when firing at manned aircraft. Others overcorrected deflection. These discoveries led to curriculum modifications. May 3, 1943. Army Air Forces Depot, Street Louis Ordnance District. Industrial logistics operated at scales that dwarfed combat requirements. Machine guns, ammunition, training films, and equipment flowed to bases in overwhelming quantities. The supply system never constrained training volume. American industrial capacity exceeded all projections. Browning produced over 100,000 machine guns. Ammunition plants delivered 3 billion rounds annually. By late 1942, the training pipeline produced more aerial gunners monthly than Germany graduated fighter pilots. This abundance represented both strength and strategy. Cost effectiveness proved remarkable. Each student cost $2,100 to train, roughly $40,000 in modern currency. That investment reduced bomber loss rates 30% compared to untrained crews. Over tens of thousands of sorties, training saved approximately 3,000 bombers and 30,000 lives. The program's cost-benefit ratio exceeded any other military investment during the war. September 1943. Statistical Control Division coded 3,200 after-action reports into standardized databases using IBM punch-card machines. The analysis consumed months but revealed decisive patterns. Average ammunition expenditure per confirmed kill fell from 12,500 rounds in early 1942 to 6,100 rounds by late 1943. 51% improvement. Enemy fighter losses increased proportionally while American defensive fire became measurably more lethal. Early combat footage showed gunners shooting behind crossing targets, rounds passing through empty air. Later footage showed tracers converging ahead of enemy flight paths. The spatial distribution of impacts shifted forward by 41%, mathematical proof of improved deflection technique. German pilots reported increasing difficulty pressing attacks. Luftwaffe after-action reports described defensive fire as unexpectedly accurate. Enemy loss rates climbed from 5% per raid to 15% by year's end. Kill confirmation reliability improved dramatically. By late 1943, American gunner credits matched Luftwaffe loss reports within 8%, the highest correlation achieved by any air force during the war. When analysts plotted accuracy improvements against training expansion, the correlation approached perfection. Every statistical measure pointed to identical conclusion. Mathematical instruction produced measurable combat advantage. October 14, 1943. Schweinfurt-Regensburg. 291 B-17 seconds targeted ball-bearing factories deep in Germany without escort for most of the mission. The second raid became the bloodiest day in 8th Air Force history. Luftwaffe fighters made over 500 attack passes during 6 hours of sustained combat. German losses mounted horrifically. 60 B-17 seconds destroyed. 17 crashed during emergency landings. 600 Americans killed or captured. But within the carnage lay validation of deflection doctrine. Bomber gunners fired over 1 million rounds, claiming 184 enemy fighters destroyed. German records documented 179 fighters lost near perfect accuracy that stunned historians who assumed combat claims always exceeded reality. American gunners achieved this under maximum stress in history's largest air battle. Operations Research Section Report Number 95 analyzed camera gun footage from 43 bombers. 72% of successful strikes originated from calculated deflection fire rather than instinctive aim. Gunners who aimed where mathematics dictated achieved kill rates triple those who relied on instinct. The best gunners maintained smooth tracking, opened fire at proper ranges, and led targets by calculated amounts. Less effective gunners jerked their turrets, fired at extreme ranges, and aimed directly at or behind targets. German fighter tactics evolved in response to American gunnery improvements, providing additional evidence of training effectiveness. Luftwaffe pilots developed slashing high-speed passes that minimized exposure time in bomber defensive zones. They attacked from 12 o'clock high when possible, exploiting the B-17's weakest defensive arc where nose guns had limited traverse. They concentrated multiple fighters on single bombers, overwhelming gunners with simultaneous threats from multiple angles. These adaptations acknowledged American defensive capabilities' increased lethality. German training manuals explicitly warned pilots about improved American gunnery, advising caution and recommending tactics that limited time under defensive fire. The enemy's reaction validated American methods more definitively than any after-action report. When opponents modified behavior to avoid capabilities they previously ignored, those capabilities had become genuinely threatening. German fighter groups that had once pressed attacks to point-blank range now broke off at 600 to 800 yards, still within American effective range, but at distances where deflection shooting became more difficult. Luftwaffe loss rates against American bomber formations climbed from 5% per mission in early 1942 to 15% by late 1943, ultimately reaching 20% in 1944. These casualties became unsustainable for Germany's shrinking pilot cadre. Strategic implications extended beyond tactical victories. Effective bomber defense made deep penetration raids feasible despite temporary absence of long-range escort fighters. American commanders could plan operations, assuming bomber formations would inflict significant losses on attacking fighters while sustaining acceptable casualties themselves. This capability transformed strategic bombing from theoretical concept into practical instrument of air power. German industry faced relentless pressure from raids it could not prevent, without suffering fighter losses it could not sustain. The mathematics of deflection shooting contributed to broader strategic calculations that ultimately defeated German air defenses and enabled invasion of continental Europe. March 1944. The technological revolution that began with classroom physics instruction reached its logical culmination as Sperry Gyroscope Company initiated mass production of the K-14 computing gunsight. This electromechanical device automated calculations that trained gunners performed mentally, embedding deflection mathematics directly into fire control systems. Based on British Mark II gyro gunsight technology, but refined for American production standards, the K-14 measured target angular rate through gyroscopic precession and mechanically adjusted aim point accordingly. The sight's operation seemed almost magical to gunners accustomed to manual deflection calculation. Operators tracked targets with the sight's illuminated reticle while rotating a range dial to match estimated target distance. Internal gyroscopes measured how fast the target moved across the gunner's field of view, calculating angular rate automatically. Mechanical linkages displaced the aiming reticle ahead of the target by amounts calculated to compensate for bullet time of flight. Gunners simply kept the pipper on target, while the sight performed all deflection mathematics automatically and continuously. Installation accelerated through 1944 as production ramped to 2,000 units monthly by mid-year. Priority went to lead aircraft in formations, the most exposed positions that faced the heaviest fighter attacks. Accuracy improved 50% in controlled testing compared to manual deflection techniques. This improvement occurred despite the K-14's relative simplicity. Later, computing sights would incorporate radar ranging, multiple target tracking, and ballistic computers, but the basic principle of automating deflection calculation remained unchanged from the wartime design. The K-14 represented the logical endpoint of a training methodology that began with chalkboard physics lessons. Instructors had taught men to calculate leads consciously, then practiced until calculation became reflexive muscle memory. The computing sight eliminated human estimation entirely while preserving the underlying mathematics. Training and technology synergized perfectly. The sight functioned best with operators who understood deflection principles and could recognize when the sight tracked correctly or required adjustment. Poorly trained gunners sometimes fought the sight, trying to aim where intuition suggested, rather than trusting mechanical computation. Well-trained gunners used the sight as designed, allowing gyroscopic mechanisms to solve problems human brains process too slowly under stress. Fighter escort evolution reduced the defensive gunnery burden by mid-1944, but did not eliminate the requirement for effective bomber defense. P-51 Mustangs could now accompany bombers throughout missions to Berlin and beyond, but German fighters still pressed attacks when opportunities arose. Bomber gunners needed to maintain defensive vigilance during entire mission profiles lasting 8 to 10 hours. Training continued without reduction, and equipment improvements continued deployment according to production schedules. American air power doctrine assumed layered defense, fighter escort as primary protection, bomber gunnery as backup capability. Both systems needed to function effectively for strategic bombing to succeed at acceptable cost. June 1945. Pacific Theater. The B-29 Superfortress introduced revolutionary fire control technology that represented the ultimate development of deflection shooting principles developed from chalkboard lessons 4 years earlier. General Electric Central Fire Control System linked 5 remotely operated turrets, 2 dorsal, 2 ventral, and 1 tail position through analog computers that solved ballistic problems in 1/20th of a second. Gunners sat at control stations viewing through periscopic sights, while electric motors aimed turrets automatically based on computer calculations. The system computed bullet trajectory, target motion, platform motion, wind effects, temperature, altitude, and range corrections faster than any human could think, then directed guns to precise aim points calculated to intercept enemy flight paths. Technical complexity approached theoretical limits for analog mechanical systems. Each fire control computer required 6,000 electrical connections, maintained under tropical humidity and temperature extremes, typical of Pacific combat conditions. Vacuum tubes, servo motors, 3-axis gyroscopes, and mechanical calculators worked together through intricate systems that pre-war reliability analysis suggested should fail constantly. Reality exceeded engineering predictions. Maintenance records documented 98% system availability despite operating environments that destroyed less robust equipment. American engineering achieved remarkable reliability through conservative design margins, redundant components, and comprehensive maintenance procedures developed through exhaustive testing. Installation procedures required specialized training. Maintenance crews attended 3-week courses covering electrical systems, hydraulic operations, optical alignment, and troubleshooting protocols. Technical manuals ran to thousands of pages describing every component and every failure mode. Spare parts logistics became critical. Each B-29 carried backup gyroscopes, vacuum tubes, and servo motors for field replacement. Despite this complexity, crews trusted the system because it consistently functioned as designed under conditions that human gunners could barely survive. Combat effectiveness validated the technology's sophisticated design philosophy. B-29 gunner teams averaged 2.7 kills per 100 sorties against Japanese interceptors, triple the rate achieved by manually aimed systems in European theater. Japanese pilots found B-29 formations nearly impenetrable when approached from angles where fire control coverage overlapped. Attack tactics that worked against B-17 seconds and B-24 seconds failed catastrophically against computer-directed defensive fire. The tactical situation in the Pacific differed dramatically from European operations. Japanese fighters possessed superior maneuverability, but lighter armament than German aircraft. They relied on sustained turning engagements rather than high-speed slashing attacks. Against B-29 seconds, this tactical approach proved suicidal. The fire control system tracked targets through complex maneuvers, maintaining accurate solutions even when fighters jinked violently. Japanese pilots reported that American defensive fire followed them through evasive maneuvers, an impossibility with manual gunnery, but routine for gyroscopically stabilized computing systems. The technological gap had become unbridgeable. The superfortress demonstrated how far American technology had advanced, from 1941 training bases, where instructors drew vector diagrams on chalkboards. The principle remained identical: aim where mathematics dictated, rather than where targets appeared, but execution had evolved from human calculation to electronic computation. Gunners still needed to identify targets, select priorities, and coordinate fire, but the system handled all ballistic calculations automatically. This division of labor, humans for tactical decisions, machines for mathematical solutions, anticipated post-war developments in fire control systems, guided missiles, and eventually computerized warfare. The B-29's fire control system represented the bridge between manual gunnery and automated weapons that would dominate late 20th century combat. September 1945. Washington, D.C. With Japan's surrender, Army Air Force's Statistical Control Division began final accounting of defensive gunnery's contribution to victory. Analysts consolidated data from 4 years of training records, combat reports, and post-war interrogations. The numbers documented systematic transformation of defensive capability through application of physics principles, industrial training methods, and technological innovation. Final statistics revealed scope and effectiveness of the deflection shooting program, with precision impossible during wartime operations. 214,000 men graduated from flexible gunnery schools between 1941 and 1945. This number exceeded total pilot production for all American military aviation branches combined, a statistic that highlighted the Army Air Force's commitment to defensive capability. The training pipeline operated with industrial efficiency, processing recruits through standardized curricula with quality control measures that maintained consistent outcomes across hundreds of schools nationwide. Graduation rates remained steady near 90%. The 10% who washed out typically failed due to physical limitations, like vision problems or motion sickness, psychological unsuitability for combat stress, or unwillingness to accept counterintuitive techniques rather than inability to learn the material. 15,399 enemy aircraft, destroyed by bomber defensive fire, represented direct combat results attributable to trained gunners. This total excluded probable kills, damaged aircraft, and fighters driven off before reaching effective firing range. German and Japanese loss records validated American claims to within 10%, the most accurate combat assessment achieved by any nation during the war. These confirmed kills represented roughly 20% of total enemy aircraft losses in European and Pacific theaters, demonstrating defensive gunnery's significant but not dominant role in achieving air superiority. Ammunition efficiency improved 42% from 1942 baseline through war's end. This improvement meant bombers carried effectively more combat capability without adding weight or reducing bomb loads. The efficiency gain translated directly into extended mission endurance and improved survival rates. Bombers that would have exhausted ammunition after 30 minutes of defensive combat in 1942 could sustain fire for 50 minutes or more by 1945, while achieving better hit rates. This multiplication of combat power through training represented force multiplication that engineering alone could not duplicate. Training cost per graduate totaled $2,100 in 1945 currency, approximately $40,000 in modern equivalent purchasing power. This investment purchased combat capability that saved thousands of American lives and enabled strategic bombing campaigns that shortened the war by months or years, according to post-war analyses. Financial officers calculated training programs' cost-benefit ratio exceeded 15-to-1 every dollar spent on gunnery. Instruction returned $15 in avoided bomber losses, reduced casualties, and improved operational effectiveness. No other training program approached this return on investment. Report AAFAN 94 provided official summary. Mathematical instruction replaced instinct. Empirical correction superseded tradition. Systematic training transformed defensive capability from desperate improvisation into calculated science. The language was bureaucratic, but the conclusion revolutionary. America had proven that warfare involved calculable problems with engineerable solutions. Complex skills could be broken into teachable components. Ordinary individuals could master counterintuitive techniques through proper instruction. These insights shaped military development for generations, while validating democratic society's fundamental advantage, the capacity to educate citizens systematically for complex challenges. Doctrinal implications influenced post-war military organization across all services. Army leadership recognized that mathematical principles could be taught systematically to recruits of average intelligence, producing measurable combat advantages through standardized instruction. This insight shaped subsequent training programs for all military specialties, from tank gunnery to artillery fire direction to radar operation. The concept that warfare involved calculable problems requiring systematic solutions became fundamental to American military thinking and distinguished Western military development from Soviet and Chinese approaches that emphasized mass mobilization over technical proficiency. Cold War doctrine emphasized technological solutions to tactical challenges, assuming superior training and equipment would offset numerical disadvantages against potential adversaries. The deflection shooting methodology provided template for this approach. When facing massive Soviet tank armies in Europe, NATO forces planned to compensate through superior gunnery training, advanced fire control systems, and better ammunition. When confronting Chinese infantry in Korea, American forces relied on superior artillery, air support, and crew-served weapons operated by better trained personnel. The pattern repeated across decades of military planning. Quality through training defeats quantity through mobilization. International influence spread through post-war military cooperation agreements. Allied air forces adopted American training methods wholesale, often purchasing simulation equipment directly from American manufacturers and hiring experienced instructors as civilian contractors. NATO standardization agreements incorporated deflection shooting principles into Allied gunnery doctrine, ensuring interoperability and shared tactical language. British, French, and Canadian forces sent training officers to American schools, observed instruction methods, and implemented similar programs adapted for their own national contexts and equipment types. Even former enemies acknowledged American methodology's effectiveness through actions rather than formal admissions. Luftwaffe veterans interviewed by historians consistently praised American bomber gunners' accuracy, attributing their respect to obviously superior training rather than natural talent or exceptional individuals. German post-war military development emphasized technical training and systematic instruction rather than traditional military culture, a fundamental shift partly inspired by recognizing what American training methods had accomplished. Japanese self-defense forces similarly adopted Western training methodology when rebuilding military capability during the 1950s, explicitly rejecting pre-war approaches that emphasized spirit over science. 1946 through 1950. Deflection shooting principles migrated into tank gunnery, naval fire control, and early missile guidance. Tank gunners learned to calculate angular lead for crossing targets. Naval fire control computers solved intercept geometry for surface engagements. Missile guidance programs implemented proportional navigation algorithms derived from deflection shooting, predict target, future position, direct weapon to intercept point. Air Force Circular 27-46 cited position prediction as fundamental to modern targeting across all warfare domains. Air Force training manuals documented deflection theory explicitly, ensuring future instructors could teach principles rather than procedures. A 1948 RAND study concluded that teaching velocity inheritance principles reduced operator error 70% across weapon systems. The last wartime training manual, Technical Order, the 1st of November 2033, closed with guidance still quoted: "Instinct kills the shooter. Mathematics kills the enemy." Men who learned to aim behind targets proved that knowledge could be as decisive as firepower or numerical superiority. August 25, 1944, marked a transformation so complete that participants barely recognized its revolutionary nature. American bomber gunners aimed at empty sky ahead of crossing targets, trusting mathematics over instinct, achieving kill rates their commanders 3 years earlier thought physically impossible. The counterintuitive technique had become reflexive through sustained repetition and battlefield validation. Muscles remembered what minds once resisted. Physics defeated tradition so thoroughly that victory seemed inevitable rather than revolutionary. The greatest testament to systematic training's success: men who performed remarkable feats forgot they were doing anything remarkable. Numbers documented the revolution with mathematical precision. Hit rates doubled from 10% to 50%. Ammunition efficiency improved 50%, extending combat endurance without additional weight. Enemy losses increased while bomber casualties declined relative to sortie rates. Statistical curves plotted improvement, correlating precisely with training program expansion. German fighter pilots acknowledged American gunnery's evolution through changed tactics, emphasizing speed and surprise over sustained attack runs. The enemy's tactical adaptation proved American methods worked more convincingly than friendly after-action reports. Opponents' modified behavior to avoid defensive fire they could no longer safely ignore. Industrial comparisons revealed strategic implications extending beyond individual engagements. American factories produced hundreds of thousands of machine guns, 3 billion rounds of ammunition, thousands of training devices, and supported graduation of 214,000 aerial gunners while maintaining full production of all other military equipment. This abundance occurred simultaneously with bomber production, fighter manufacturing, artillery fabrication, vehicle assembly, and ship construction. German and Japanese industries struggled to maintain fighter production while facing resource shortages, transportation collapse, and overwhelming Allied strategic bombing. American training systems represented competitive advantage as decisive as radar, proximity fuses, or nuclear weapons, perhaps more decisive because training multiplied effectiveness of every other technological advancement. Scientific legacy established principles that dominated subsequent military development across decades and conflicts. The deflection shooting methodology proved that complex problems could be broken into teachable components through systematic analysis. It demonstrated that standardized instruction produced measurable results regardless of individual student background or aptitude. It showed that ordinary individuals could master counterintuitive techniques, requiring suppression of natural instincts through proper training methodology. These insights shaped Cold War military education, influenced civilian technical training, and contributed to broader understanding of human learning, applicable far beyond military contexts. The gunnery program demonstrated democracy's fundamental strength in ways that transcended immediate combat effectiveness. Free societies could identify problems analytically without ideological constraints. They could apply scientific principles regardless of whether solutions contradicted traditional practices. They could mobilize industrial capacity efficiently through market mechanisms. They could educate citizens systematically without regard for social class or political reliability. Totalitarian societies struggled with all these capabilities, constrained by ideological rigidity, command economy inefficiencies, and social hierarchies that limited educational access. American aerial gunnery training exemplified democratic advantages that proved decisive across entire war. Today, aviation museums display cutaway turrets, showing confined spaces where young gunners learned to calculate angular rates while fighters attacked at lethal speeds. Restored B-17 seconds and B-24 seconds carry visitors who marvel at visibility limits, physical demands, and psychological stress that World War II aircrews managed routinely on missions lasting 8 to 10 hours. Historical footage shows tracers converging ahead of enemy flight paths, visible proof that men learned to aim where mathematics dictated rather than where instinct suggested. The physical artifacts remain as testimony to transformation from desperate improvisation to calculated science. Interactive exhibits demonstrate deflection shooting principles using computer simulations based on wartime training devices. Visitors sit in mock turrets, track projected targets, and receive scores based on their aim points. Most fail initially, their natural instincts leading them to shoot behind crossing targets, just as untrained recruits did in 1941. Those who study instruction panels and apply deflection principles improve dramatically, experiencing firsthand how education overcomes instinct. The exhibits teach history through participation, conveying lessons more effectively than passive observation of static displays. On any given mission between 1943 and 1945, American bomber gunners aimed behind crossing targets, fired at empty sky where mathematics predicted interception, and hit enemy fighters because physics demanded that solution. They transformed defensive gunnery from lowest priority specialization into lethal capability that German and Japanese pilots learned to respect and avoid. They proved that education could defeat instinct, that industrial society could systematize skill development, and that ordinary young men could master extraordinary challenges when properly trained. The revolution occurred so systematically that it appeared inevitable, the highest compliment any training program can receive. The men who aimed behind their targets rarely discussed their counterintuitive technique after returning home. They spoke instead of friends lost, missions flown, and relief at survival. But embedded in their modest accounts lay evidence of profound transformation. They had learned to trust mathematics over instinct, calculation over tradition, and systematic training over natural talent. These lessons extended beyond aerial gunnery into post-war careers where analytical thinking and technical education provided advantages their father's generation lacked. The gunnery schools taught more than deflection shooting. They taught that complex problems yielded to systematic analysis and that ordinary people could accomplish extraordinary things through proper education. If you value detailed military history that reveals how victory emerged from systematic preparation rather than spontaneous heroism, please consider supporting this channel. Every contribution helps preserve these stories for future generations, who should understand that democratic societies prevail not through tradition or force of will, but through capacity to identify problems analytically, apply knowledge systematically, and educate citizens to unprecedented capability. The men who learned to aim behind their targets demonstrated that knowledge properly taught and diligently applied defeats instinct, tradition, and numerical superiority. Their success established principles that remain relevant wherever complex challenges demand systematic solutions.